Okay, so I'm Doug Smith from the Met Office, and I'm going to show you some results about predicting atmospheric circulation signals, especially in the North Atlantic. And what I'm going to show you is that the models tend to underestimate the predictability of these atmospheric circulation signals by a large amount, an order of magnitude. So consequently, the uncertainties are greatly overestimated. So the results I'm going to show are diagnosed from decadal prediction experiments. But if this process, or if this underestimation of the signal extends beyond 10 years, and we think it might do, then these results will actually affect all of the work packages. In terms of how do we combine initialized and uninitialized simulations? Do we need the storyline approach? Things like that. So I'm going to talk about atmospheric circulation predictions. So just to illustrate the kind of present situation in terms of projected trends in the North Atlantic and the huge uncertainties that we find, what we have here is projections from the NCAR climate model, and these are just two different ensemble members that differ by tiny perturbations to the initial state. Okay, so they have the same external forcing and really tiny perturbations. And what you can see in this is completely opposite projections for the coming 30 years. So on the left, we have kind of a negative North Atlantic oscillation, so the contours of the sea level pressure, and the colors are the temperature. So we have a cold Northern Europe, and on the right, we have the opposite with a warm Northern Europe. And since these only differ by tiny perturbations to the initial state, the conclusion is that this is due to irreducible internal variability. So this is like a perfect model study. So the conclusion for that really is that in terms of projecting European winter climate, then it's not too promising really. So what I'm going to show you now is results from decadal climate prediction experiments. The black line here is the observed time series of the North Atlantic oscillation. This is 8-year running means. Okay, and you can see that it's dominated by this increase from the 1960s to the end of the 1980s, and then a decrease after that. The red line, the thick red line, is the ensemble mean of a large ensemble of decadal prediction experiments. These come from CMIP5 and CMIP6. There are 14 models, 169 ensemble members, and you can see that really they don't show any strong signal at all. And the pink shading is the ensemble spread from all of these ensemble members. And you can see that similar to the climate projections, we can find some ensemble members. So the observations for this peak period show a very clear warm Northern Europe, and we can find some ensemble members that show the same pattern and others that show the complete opposite. So based on this picture and taking the models at face value, we would assume, we would conclude that there isn't really any scope for predicting the North Atlantic oscillation and hence European winter climate on decadal timescales. But we can actually test this more thoroughly with decadal predictions because we have all the hindcast experiments. We can assess the skill more thoroughly. And so what I've plotted here, so the left-hand plot was the one you just saw, and the right-hand one now is if we actually scale this up to have the same variability as the observed time series. And now you can see that the decadal predictions do actually remarkably capture most of the signal. So we do now find the increase in the NAO from the 60s to the end of the 80s and the decrease after that. And actually the correlation here is nearly 0.8. So it appears that there is potentially a lot of skill in this decadal prediction systems that we didn't see if we just take the models at face value. But there is a discrepancy here. So a correlation of 0.8 or 0.79 should explain 62% of the observed variability. And clearly on the plot of the left, it explains almost none of the observed variability. You really can't see much of a signal there. So basically the magnitude of the ensemble mean variability is inconsistent with the high correlation score that we're seeing there. So it's really shown that there's some sort of inconsistency, some sort of error in the models. This has been seen before on seasonal timescales especially, and it's further illustrated by this plot here, which shows the skill of the ensemble mean prediction against the observations in the black line against the number of ensemble members that are used to make that ensemble mean. So as we add more ensemble members, we're averaging out some of the noise in the predictions, extracting the signal. So you can see that the correlation does increase as we add more members to the ensemble mean, so that's expected. What's not expected is this blue line, and now this is where we, instead of measuring the skill against the observations, we're measuring the skill against one of the individual model simulations. So we're treating that simulation as the observations and trying to ask the question, can the model predict its own evolution of one of those members? And we find now that the skill of the model predicting itself is much, much less than the skill of the model predicting the observations. So that's kind of paradoxical in some ways. You know, you would expect a model that is a perfect representation of itself to be able to predict itself much better than it can predict observations, because clearly there are errors in models. So it means that members are not alternate realizations of the observations. We need a very large ensemble to extract the predictable signal. You can see the skill rising steadily as the number of ensemble members increases. And really this undermines the basis of ensemble prediction and treating the different model simulations as potential realizations of the observations, as we have been doing. It turns out that this paradox is actually quite simple to understand. So if we imagine that there is some predictable signal, this is a highly idealized example, obviously. So let's imagine that the predictable signal is this kind of sine curve, and it has the variance sigma s squared. On top of that signal, there will be some noise. So what you will actually observe could be something like the black line, which has a greater variance because of the noise added onto the predictable signal. So that's a kind of idealized situation. So on the left, we could have, this could be what it looks like in the observations, with a large predictable signal, sigma s squared, compared to the total variability. So a large fraction of the total variability is predictable in the observations. Whereas in the climate model simulations, it appears that the fraction that's actually predictable is much, much smaller than in the real world. So we can actually quantify this predictable component. So it's essentially the predictable signal divided by the total variability, so sigma s divided by sigma. So we're defining that as the predictable component, and we can measure the ratio of the predictable components in the models and the observations. So in the observations, that predictable component is simply the correlation that we can already achieve with our imperfect model forecasting system. So the anomaly correlation, or R squared, certainly we've just taken the square root for convenience, gives us an estimate of the predictable component in the observations. Now it should be greater than that, because if that's how much we can already predict with imperfect models, then we would expect it to increase as the models get better. The predictable component of the models is simply the variance of the ensemble mean. That's where the predictable signal is, divided by the variance of individual ensemble members. And then we can take that ratio to give us a ratio of predictable components. If everything is right in the models compared to the observations, then this ratio should be 1. So the same amount of predictability in the models and observations. If it's greater than 1, then that's showing that the observations are more predictable than the models are telling us. And then we can convert this ratio of predictable components into the ratio of predictable signals. And it turns out if the total variability is the same in the observations and the models as it is, then this RPC, this ratio of predictable components, is simply the ratio of predictable signals. So now going back to this plot that I showed you before. So on the left again, you can see very small signals, and on the right, the variance adjusted one. And what I've plotted also is in the thin line is the ensemble mean of the 169 members. So this is the same line now as the one on the left. You can see that it does simulate or predict an increase in the NAO and a decrease after that, but you can see that there's an awful lot of noise on this thin red line, lots of internal variability that shouldn't happen in 8-year running mean. So this is unphysical. So what I did to get the thick red line here was some lagged averaging of the hindcast. So I took the latest 4. So for each hindcast start date, I take the hindcast that starts at that date and the previous 3 and average them together, and now you get a much smoother curve and a higher correlation. This now has 676 members in this ensemble mean. So really this is showing that there's really way too much noise in this model ensemble, but there is a predictable signal there, which you can extract if you can average out the noise with enough ensemble members. So it turns out that this ratio of predictable components, the ratio of predictable signals, is 11 for decadal predictions of the NAO, suggesting that the signal is an order of magnitude too weak. And now, because each ensemble member reduces the error variance, so that discrepancy in the signal must be squared to understand the number of ensemble members that's actually needed to reduce it, to extract the predictable signal. And so it turns out that if the signal is an order of magnitude too weak, then we need 100 times, 2 orders of magnitude more ensemble members to extract this signal. So that's a huge thing to kind of appreciate. So we can plot maps of this ratio of predictable components. Remember, anywhere where it's greater than 1 shows that the models are underestimating the signals. And here are maps for temperature, precipitation, and sea level pressure in these decadal forecasts. So the problem is actually very widespread on decadal timescales. Even for temperature, we're seeing RPCs greater than 1 in many regions. And then you can see the colors get stronger. 10 minutes. Colors get stronger for precipitation and for sea level pressure, showing that it's really a kind of atmospheric circulation problem, because that's what really affects precipitation. But it's widespread. It's not just seen in the North Atlantic. We see it in other regions as well. So what we really want, so we've shown that the North Atlantic Oscillation is highly predictable actually on decadal timescales, much more so than we previously thought. But what we want to do is predict the impacts of the NAO, especially on European climate and the east coast of the USA. And of course, the impacts in the real world are very strong for the North Atlantic Oscillation on European winter climate. So what I've plotted in the left is a typical situation where we have a strong North Atlantic Oscillation in the observation. So we're getting warm air advection into northern Europe, cold air advection into southern Europe and northern Africa. So this typical pattern, this dipole pattern with a warm northern Europe and a cold southern Europe, North Africa. And then on top of that, there will be some warming from greenhouse gases shown by these red arrows on the top. Now, in the ensemble mean forecast, although the North Atlantic Oscillation phase is predicted, the magnitude is underestimated by an order of magnitude. And so these arrows that I've shown for the winds, the yellow and the blue ones, are much smaller than they actually should be. So those are too small. So we're not getting the impact of the atmospheric circulation anomaly on the European climate in these decadal forecasts. And what we're seeing is what's left over, which is mainly greenhouse gases. So the ensemble mean, the mean of a very large ensemble, although it's good for predicting the phase of the North Atlantic Oscillation, highly skillful, it is not skillful predicting the impacts on Europe, for example. So you can see that in this plot here. So what I'm trying to predict now is this peak in the North Atlantic Oscillation that occurred in the late 1980s, highlighted by the green circle in the lower left panel. So the top row shows the observations during this peak North Atlantic Oscillation phase. So you can see a clear quadrupole pattern with a warm northern Europe, a cold southern Europe, northern Africa, a cold northeast USA, Canada, Labrador Sea area, and warm southeast USA. And associated with that, there is a quadrupole in rainfall anomalies. And then the right-hand plot just shows the sea level pressure anomaly for this peak. This extreme phase of the North Atlantic Oscillation. And then the middle row shows the same thing in the ensemble mean, the forecast, and as expected, we don't really see a signal. So it's very, very bland and nothing to see there. But if we rescale that signal to have the same variance of the observations, now as I showed you, we do see the North Atlantic Oscillation pattern, but we don't see the impacts in terms of temperature at all, for the reasons I talked about before. But of course, there are some ensemble members that do capture the right connection between the North Atlantic Oscillation and European climate. So the one on the right, for example, shows this dipole pattern: warm northern Europe, cold southern Europe. So the question is, can we select those members that have the correct magnitude of the North Atlantic Oscillation to make a better forecast? So we've come up with this NAO matching technique. So I've said in reality the NAO dominates over greenhouse gases. but it's too weak in the ensemble mean, so the greenhouse gases are dominating incorrectly in the model ensemble. But can we choose those members that have the correct magnitude of the NEO? So we do this by using the ensemble mean to find the actual NEO signal, by getting rid of all the noise and finding the signal, and then adjusting its variance for the fact that the signal is underestimated. And then we look within the large ensemble that we have for those members that are close to the actual magnitude of the signal that we want, and we only use those members. And if we do that now, this middle panel, you can see that now these members that have the correct forecast magnitude of the NEO do indeed capture much of the observed extreme pattern of variability, the quadrupole pattern. So this is one way to deal with the model error that we're left with at the moment. Of course, what we really want to do is fix it at source, and there's still a lot of work to be done to understand what's causing that. So just to summarize then, it's a kind of a tale of two things. So the good news is that climate is much more predictable than previously thought. The NEO correlation is 0.8 in decadal predictions. But the bad news is that there is a serious deficiency in the climate models. The predictable signal is an order of magnitude too small, which means we need 100 times the number of ensemble members to extract the predictable signal. We don't yet know the cause of this model deficiency, and then particularly we need to work out, what is its effect on projections beyond 10 years. We've seen it in seasonal, interannual, and decadal timescales now. We believe it would also impact further down that. Potentially also impact the response to external forcings. So I'll leave it there. Thank you. Thank you.
Thanks, Doug. That was really interesting. What do you think when you look beyond 10 years you will see? Out of interest, if you were to speculate on that.
Well, I think we'll see the same thing, and there's lots of evidence in the literature that the models underestimate the response to external forcings, including solar, volcanoes, ozone, for example. So I think we'll see the same thing.
Okay. Have we got time for one question while we load up the next presentation? Let's see if there are any hands up.
There are no hands up and no questions in the chat. If anybody does have,
yes, if I may, I don't know where to raise my hand on the panel.
Don't worry, Robert, ask your question.
Oh yes, thank you. So thank you for the presentation. So there is a lot of emphasis on enhanced predictability, as I understand, with a high number, which is 0.8. But if I understand well, this 0.8 is based basically on one bump of a time series which is well predicted in one area of the world. So I would be much more comfortable if there would be some other cases, either in time or space, where we could see the same situation actually. And my other question is how much this score depends on the filtering that you are doing with the averaging with previous forecasts. It seems to be extremely dependent on this. Is there any reason why increasing the number of members is apparently not helping, why averaging with previous forecasts does help, if I understood well? I'm not sure to have well understood. So yeah.
Okay, I'll try to remember some of that. So in terms of the averaging, we only have 169 ensemble members. So, and the correlation for those 169 was 0.48. Still highly significant. I should say that we have tested the significance, using the standard methods, block bootstrapping, to allow for the autocorrelation, and the p-value is less than 0.01. So for the number of ensemble members that we have is 0.48. We can't add any more because we don't have any more. The only way to do that is to use previous forecasts, and then it rises to 0.79. I've tested different lags, and it's not overly sensitive to that. In terms of whether we see this issue in different time and space scales, then absolutely we do. So I showed you a map of the RPC, the ratio of predictable components. I showed you that it affected Sahel rainfall, for example, and many regions outside the North Atlantic. And in terms of different timescales, this problem was first spotted in seasonal forecasts of the NAO. It's since been found in interannual forecasts of the NAO, in forecasts of European summer rainfall on both seasonal and multi-year timescales, forecasts of Sahel rainfall on multi-year timescales, and you can even see it in sub-seasonal timescales in terms of the MJO teleconnection pattern. So it's a widespread issue in both time and space, I would say.